guys, this is day 14 of our daily push-up challenge. So we've been doing this for 2 weeks now, 11 more days to go and we're done. This time, the problem we'll solve today will be a Putnam problem from 1939, the oldest one yet, you know. And before we read it, let's insert one push-up in there. I mean 5, 1, 2, one set of push-up, 3, 4, 5. Okay, so we write our progress right here, and then we read the problem. Find the length of the curve y squared equals x cubed from the origin to the point where the tangent makes an angle of 45 degrees with the x-axis. So initially, what we can do is we can draw that up. We can study this particular curve, how it looks in the in our real plane. You know. So look. If your x have negative values, since you're getting it, you're cubing them, the right hand side will still be a negative, but for real numbers, okay, the right hand side will always be positive, right? So therefore, our curve will be constrained on the right hand side of the Argand plane, on our real plane, right? So for example, our 0, 0, of course, satisfies the equation. Another point that satisfies the equation is the point 1, 1, because when you take the cube of 1, that's also equal to the square of 1, okay? So maybe the cube looks something like this, okay? But note that this is the positive half of the curve, because the curve is equal to, you can write it as plus and minus square root of x cubed. So you have the negative component, which also solves this point when y is equal to negative 1, because the square of negative 1 is also 1. So this point also solves the equation. So maybe you have a curve that looks like that. So this is like the lower half, the y equals negative square root of x cubed portion of the curve. So now we want we want to get the length to a point where a tangent makes an angle of 45 degrees. That's only possible in the first quadrant, right? Because in the first quadrant, the angle that the tangent makes can be 45, while in the fourth quadrant it can't be, right? So we take the function y equals not 3 halves, y equals x to the 3 halves is what I meant to write. X to the 3 halves. Okay, so let's continue. 6, 7, 8, 9, 10. Okay, so we have 10. So what do? We take the derivative, because as you know, the derivative of a function, if you gives you the slope of the curve at the particular point. So if you take a point, you evaluate that point at the derivative of the function, that the resulting expression will be the equation of the line, okay, that is tangent at that particular point. Okay, I mean the line tangent to that particular point will have the equation given by the derivative. So this derivative is equal to 3 halves x to the 1 half, and of course this particular line, okay, its slope is also equal to the tangent of the angle it makes, the inclination it makes with the x-axis. So in other words, this is equal to tan of the angle. In this case, this is 45 degrees. This is just equal to 1. Let's call this this particular point that meets a tangent line which has a slope equal to the tangent of 45 degrees. Let's call that x naught. Okay, and in fact, a fun trivia, the tan, or the word tangent, it actually comes from the Latin word tangents, which means to touch, you know, because your line is touching your curve at a particular point. But anyway, yeah, so we can solve for this x naught now. This is just equal to 2, no, not 2 over 3, because you're gonna square it, because x naught is to the 1 half. So this will give you 4 over 9. Okay, so let's continue. 11, 12, 13, 14, 15. Okay, so what happens next? Now we know the point where we want to measure the length of the curve. We want to measure it from the origin to the point whose x value is 4 over 9. So any arbitrary curve, let's say like that, okay? Let's say from the point A to point B. How do you measure that length in the first place? Well, that's given by calculus. You take like an infinitesimal length ds. You take an its infinitesimal x component dx. Its infinitesimal y component dy, and you use Pythagorean theorem. Ds is just dx squared plus dy squared, and then you take the square root. And then if you want to take the entire length, let's call it s, you're just integrating. Okay, you're adding. When you integrate, you're just add. That's why the symbol for integration is just a stretch s, which means sum. You're just summing all this infinitesimal ds, right? So you're summing them from a to b of ds, which is just equivalent to the integral from a to b of square root of dx squared plus dy squared. Okay, and usually in order to utilize this, you can write this in two ways. It depends if you're given x as a function of y or y as a function of x. In this case, we're given the latter, so we can what we can do here is we can factor out dx. Okay, so we can write the inside the square root will become, we factor out dx squared inside the square root, that becomes 1 plus dy over dx squared. And then outside the square root, dx squared will just become dx. Okay, so now we're gonna use this equation to solve for the length of the curve in our problem, because we know the starting point, the origin, we know the end point, which is 4 over 9. So we're now at 11, 12, 13, 14, 15. Okay, 15. So now we just evaluate from 0 to 4 over 9, the square root of 1 plus the square of the derivative of our function. So this is just the square of the derivative of our function is 9 over 4x. So this is already the square. Okay, and then you have dx. Okay, so since inside the square root it's just linear in x, this integration is trivial. You let everything inside is equal to u, and then you get a factor of 4 over 9. Okay, from the substitution or changing of variables, and then you get a factor, so the entire thing u will be raised to 1/2. When you take the integral, that becomes u to the 3/2 over 3/2, or you get a factor of 2 over 3. And then now you will be evaluating 1 plus 9 over 4x to the 3/2 from 0 to 4 over 9. Okay, so we're now at 15, 16, 17, 18, 19, 20. Let's finish it. 21, 22, 23, 24, 25. Okay, man, they're getting red again. So I must protect my hands. You know, it's how I make my living, solving stuff. You know, and coding stuff on the computer. But anyway, so we evaluate this. So this is just mindless algebra. So this is just 8 over 27. So we evaluate 4 over 9 first. My fiance is trying to have a video set, so let's go back to that later. You have 1 plus 9 over 4 multiplied by 4 over 9 is just 1. Okay, to the 3/2, and then minus, you evaluate this at 0, this is just 1 to the 3/2, which is just of course 1. So finally you get 8 over 27. Okay, and then you have 2 square root of 2, so because that's just 2 to the 3/2 minus 1. Okay, and there's the length of your curve that we're trying to look for. Okay, but anyway, yeah, that's it, guys. This has been day 14, our second week of push-up while solving Putnam problems. We have 11 more set of push-ups to do, but more excitingly, 11 more Putnam problems. So thanks for watching. See you next time, and bye-bye.